This is another problem, lecture 6 in fact, to describe the application of describing function to examine the the stability of some nonlinear system. So this is the problem. Here nonlinearity is the saturation amplifier and Planck function is this one. We have to determine the largest value of k for which the system is to stay stable, and the next part of the problem is we have to find the frequency, amplitude and nature of limit cycle for gain k is equal to 3. So to start with, as we all know that we have to have in fact the plot of describing function, and we have to have a not describing function minus 1 by nx as x varies between 0 to infinity and the Planck function. So here trick is to adjust the gain of the saturation amplifier k with the Planck function. So just see, this has been adjusted, and so the Planck function right now has become this one. So this one is equal to this one, and this is its magnitude portion, this is its phase portion, and this table shows the variation in m phi as omega is varied. At omega is equal to 0, we can see it is infinity, phase minus 90. At omega is equal to 1, this is k by root 10, and phase is approximately minus 200. At infinity, this one is this one. So the plot is something like this. Now at this point, okay, we can see that phase equal to at real axis, in fact phase equal to minus 180 degree. So that has been determined, that is at A phase is equal to minus 180 degree. So phase set to equal to minus 180 and has phase test the omega is equal to 1 by root 2 radian per second. The describing function we all know of this nonlinearity is this one, and as k has been adjusted with gs, so this one is minus 1 by nx. So the table for x is equal to 0, minus 1 by nx is not acceptable until x becomes 1, at which this one is minus 1, at 2 this is minus 1.5, and this continues. So the plot is like this, starting from minus 1 and it moves leftwards, and the magnitude of kj omega is equal to 1 for determining the optimum value of k for which the system would stay stable. And after setting this value omega taken right from here, we get the result that for k is equal to 3 by 2, the system is going to stay stable. That is, optimum value of k is equal to 3 by 2 is the result. Now next part of the problem is we have to determine the frequency, amplitude and nature of limit cycle for k is equal to 3. So we have set k is equal to 3. Now we again talk about the intersection of kj omega plot and minus 1 by nx plot, and they are going to intersect, as we can see, at point B. So at point B, again we know that the limit cycle frequency is going to be this one, because we are still on real axis, and the amplitude could be determined by setting this relationship. 3 is the value of k, so k j omega, so this one, and g j omega is, we all know, at this is 2 by 3, and after fetching these values and solving, we get x is equal to 2.5. So for k is equal to 3, the intersection occurs at B. We can see here, intersection occurs at B. It can be observed that as an observer traverses g j omega in the direction of increasing omega, the portion BO lies to the right. So it represents unstable operation, and the portion BC lies to the left. So it represents a stable operation. So at B, the limit cycle is going to represent a stable operation with amplitude k is equal to 3 and omega is equal to 1 by root 2 radian per second. I hope you must have understood the concept of stability determination by describing function method, which was another illustration in that sequence. Thank you.